Okay, welcome to another interview with the Zero to ASIC course channel. And today I'm joined with Will, who you may know as Will Flux on Twitter. And did I get that right, Will?
Yeah, it's Will Flux. It
Yeah.
seems like a nice name.
Yeah, so could you just give us a little bit of background about yourself?
Okay, like sort of professionally, I do sort of software technical architecture, DevOps, cloud. Not really relevant to this kind of discussion, but a few years ago, a friend of mine, Ben, uh, pointed me at FPGAs and said, take a look at this. And I got myself. It turned out a very ancient board that did have, not great tools and everything. But I could almost see immediately these things were amazing. So I was like, got to do more with this stuff. So I eventually got myself an Arty board, which was a decent board with modernish tools. The open source tools were a bit, well, I didn't really know about them at the time. And so, yeah, I started trying to get my FPGA boards to do stuff. So I guess
Cool.
that's how I kind of got into the FPGA stuff. But I've always been into like graphics and computers demo scene. Started out on the Amiga as my first computer, really, the first computer I bought. And some of that spirit I've sort of tried to capture in when I've been working on the FPGA.
Yeah, so we were just talking about the kind of relevance, and I was saying that I saw your tweet about your FPGA project on Twitter and had a look through your site, and I thought it looked like a really good resource. And then we were discussing the possibility of doing this interview, and for me, the context is that on the Zero to ASIC course, we get some people with digital experience, but a lot of people with nothing. So then I wrote a part two, section 2 of the course is all about digital design, and I'm using the Icebreaker board from 1-bit-squared as the kind of, if you can do it all with simulation, but if you want to do it with hardware, then that's the board I recommend. And so, yeah, I was really interested to see your take, and I think that graphics projects are a nice way of learning FPGAs, and they kind of showcase something that's a bit difficult to do if you're coming from, say, the Arduino or microcontroller world. It's quite difficult to get the timings you need. I mean, people have done it, but it's quite difficult to do something impressive or particularly real time. So maybe you could tell us about the Project F aim.
Okay, yeah. So Project F kind of really sort of started about a year ago when in fact, thanks to COVID, the work dried up a bit and I had a bit more time. And I'd already written a few blog posts about my FPGA experience. And after my initial enthusiasm, you may have got in the introduction, I kind of hit, I think lots of people do this kind of barrier that even quite simple things, it's really hard to find out how to do them because there are kind of no examples. So, you get your Blinky working. That's what, you get a Blinky example, LEDs working. Now what next? And I bought books and I dug through forums and stuff, but it was really hard to do things that if you're doing stuff on Arduino or Raspberry Pi or whatever, there'd be loads of resources. There were basically no resources almost. So basically Project F was, I'm trying to sort of share my hard-won learnings and build some enthusiasm for FPGAs. And because of my sort of background of interest in graphics, and as you say, graphics are very hard to do well on a microcontroller. They seemed ideal. And I'm very much also believe in, learning by doing and experimenting and things. And so the graphics provide a nice, fun, interactive way to see what you're doing and work with even the smallest boards like the Icebreaker, which I've been porting my designs to. So
yeah, because I mean, for people that haven't tried video, it can, I don't know. The first time I did it, I thought this is going to be really difficult, and then basically it's 2 timers. So at least for VGA, so it's actually not that difficult.
Yeah, I'd use the analogy with CPU design. Like before you've heard about it, you think it's incredibly complicated. Then you get some book and it's like, oh, here you can create a CPU in a few, simulate it in software in a few hundred lines of code or in a small amount of Verilog, a really simple CPU. And similarly, very simple graphics are very simple. But obviously, as you get into more complex stuff, once people say, "Oh, build a GPU," that's quite a big ask. So,
Yeah.
But yeah, graphics. The core stuff is really quite straightforward, and So yeah, it does seem like a great introduction, a way to learn how to use FPGAs practically.
So I'm interested to know how you describe what an FPGA is for someone who hasn't used one or doesn't know what they are. How would you describe that?
Yeah, this is one of the most difficult questions. I mean, I talked to lots of my technical friends about this project when it's kind of getting underway, and I couldn't. It's really hard to convey what an FPGA is. I think my best answer is I've just got it like a giant virtual breadboard. So if you're familiar with electronics, you're used to having all your individual components and not gates and gates. It's like that, but on a huge sort of virtual scale, or maybe more simply, like Lego for electronics. So you can, or for digital design. So you can, you've got your individual components, your RAM and your multipliers and your logic gates and things, and the FPGA lets you build those sort of really quickly and simply compared to what you'd have to do if you were building, it from scratch using individual components. You can build at a much larger scale. So, and I guess if you want to get really enthusiastic, then you say, well, you can do everything that Apple and Intel and TSMC can do, a bit slower, and you've obviously you need to learn design skills, but you can build a CPU, you can build a graphics card, you can build a crypto miner, a robot controller, all that stuff. There's nothing your FPGA can't do that, all the big boys can do at a bigger scale and faster, but you can do that too. So if you ever had to be Jay Miner or Steve Wozniak or whatever, I think this is the kind of modern way to have you go at building something new and innovative.
Yeah, and I like the Lego metaphor as well. I often use that one. And then now when I'm trying to explain ASICs to people who use FPGAs, I'm like, okay, well, imagine you've got this like single block of Lego that we were using in an FPGA that's like a lookup table or a flip-flop. And then you zoom into that and you realize that one Lego brick is made out of 100 other tinier bricks. And that's like what building stuff with an ASIC is. You've got that finer layerful of detail. So in an FPGA, you use a lookup table to model an AND gate, and maybe you're wasting resources because you have to build a big one out of lots, and then you can't use some of it, or you only need an inverter and you waste the whole lookup table on one function. But then in an ASIC, you have like 150 smaller, tinier Lego blocks, and one of them is just a single inverter, and the other one is like an 8 input AND gate. So you'll get finer grain access to the raw materials, and so you get more efficiency, and your shapes that you're building out of Lego are smoother. But yeah, the major downside is the 6-month lead time, and if you get it wrong, then you can't fix it afterwards. So FPGAs for the win. So we've already like touched on this, but what's your kind of sense about a good way of teaching FPGAs?
Okay, well, I'm definitely, as I mentioned, for the hands-on doing practical stuff. I think most of us, when we learned software programming, lots of people did that, at school, teenagers or whatever. You didn't learn about CPU pipelines or, speculative execution or any of those kind of things. You built a program to, draw graphics on the screen, make your own little game, do a word quiz or whatever. You did practical hands-on stuff, and the kind of theory you pick up as you went along. And I very much believe that's the right way to learn FPGAs too. There is because most of the material online you find is aimed at sort of academic audience, for sort of later years of undergraduates or graduate students. It tends to be very theoretical and quite dry. Whereas I think the way people get into electronics, Arduino, open source, whatever, is by doing practical things and by learning, by seeing and doing. And so that's why I'm really keen on projects like doing stuff with graphics. And there's a few good examples with FPGA for Fun, which is another site I'd recommend, which talk about, audio, doing stuff with PCI Express. Even they've got lots of practical things. So I think you pick up the theory as you do that. Otherwise, I think it's way too off-putting if your first lesson is here's a blinky LED, now let us explain the difference between a Moore and a Mealy, finite state machine. You're like, what? That's too abstract. You want to learn practically, is my view. But different people learn in different ways. This is my take, I guess.
Yeah, I'm definitely on the practical side of things. When I think back about like the stuff that I remember from previous years, or like even kind of formal training, like going to university to study this kind of stuff, the things that I remember most clearly are the things where I actually had to build something or solve a problem, where I was fully kind of involved, and that hands-on somehow works really well for me. I was looking over a blog post I wrote a while ago about my process when I started on FPGAs kind of 3 or 4 years ago. And I'll just tick these off. So I said, find a mentor, find a community, find the tools. Because at that point, I was just transitioning from like the huge kind of multi-gigabyte downloads to the open source tools, which worked much better for me because I'm like a command line makefile Vim kind of person. So I much preferred those. Find how other people do it, like look at how other people set things up. Start a project. So I did like a video. I'd previously done an interactive kind of virtual graffiti style project where you use a spray can and it uses an infrared camera to track where that is and put it on the VGA screen. But that always took kind of 100 milliseconds latency with a computer in the loop. So I decided I'm going to do this as an FPGA to try and get that latency down. And I thought that was going to be, a short project, but it took over a year to complete that. And then document and present the project. So then I took it to a maker faire and showed that off. Study other people's work. So I looked at how Luke Valenti's USB bootloader worked for the tiny FPGA. Because that was like seeing the way he did that and his test benches was really eye-opening for me. And then start teaching. So I started a group at the local Valencia hackerspace to start kind of teaching this stuff and stay like 1 or 2 steps ahead of the people on the course. So it seems to me like with Project F, you've kind of, well, you've got like you're doing the split between the Arty and the Icebreaker, aren't you? So you've got the tools there.
Those are 2 boards that seem popular, and I've chosen to support them. But first, I tried adding more boards, but especially as my design. I mean, initially, I thought my blog post, I'd just write a blog post, move on to the next one. But I keep returning and improving and working on the designs and explanations as I've been learning myself. And I found if I tried to support too many combinations, just the testing became. It would take me a day just to test with all the combinations of stuff. So I want to support the open source tools and the Icebreaker boards, but I also know quite the Arty board and Xilinx is quite popular as well. Although there is improving, the tools for open source and Xilinx are getting there. So I thought it was good to support both, and it also helps me avoid falling into the trap of using, vendor specific stuff. My designs pretty much work well on both, though I have had to tweak things. When I was porting to the Icebreaker, I guess tying in with what you were saying about learning or teaching, I think teaching yourself or trying to teach others is a great way to learn too. I mean, I've learned so much by, posting my ideas and designs and then getting feedback from people. And I think finding the 1-Bit Squared Discord channel, which I did about a year ago when I got my Icebreaker, that's made a huge difference.
So that's the kind of feeds back into this like community idea, also, and then finding people on there who really know what they're talking about. That's really helpful.
Yeah, and to prepare, there are people on there who, whose knowledge is so far above mine. It's, we're sort of in different worlds when it comes to digital design, but they've been great in helping me, and I try and help the community obviously by publishing examples and making this stuff accessible, because often people are like, well, here's an example. You point you at a Git repository and, here's 50 Verilog files and a token README. And you're like, well, how do I even start? Where do I begin? And so, I'd encourage other people, if you're learning, to, blog and write about it. people will really appreciate it. Even things you think are basic, like read memh, the Verilog, loads stuff into memory, has been the most popular post on my blog since I did it. Even though you think it's a really simple, trivial thing, but it seems so many people are searching for how to use this seemingly simple thing. So yeah, I'd really encourage people to put their learning and ideas out there. That there is not that much on the internet for FPGAs for enthusiasts.
And a lot of it is pretty old, or it's only going to work with like some specific vendor tools. So whenever I search for read memh, I always get onto this same like super old school web page that doesn't really help me with what I'm trying to do. Yeah, but I still struggle with that kind of stuff, especially when I want to read a file from a different directory. It's like every tool kind of needs the text file that it's reading in a different directory, and I end up having to have symlinks everywhere, so it always works.
Yeah, it was those kind of problems. I couldn't get Vivado. I had my file in my project, whatever, but it turned out it just gave this error. There were no internet matches for it. And so I put that in my post. I think that's partly why I get lots of traffic to just that post, because it turns out once you know how to do it, it's really straightforward. And I think this is a really important thing for people to know when they're coming to FPGAs. They'll be told, hardware design's hard. You need a different mental approach, and it's nothing like software and whatever. And that is true, but lots of the stuff just comes down to digging out the right information, which unfortunately is harder than, I'd like, and I think most people would like. But having the community, certainly, I'd say the getting to know some of the people on 1-bit squared.
I would definitely really echo that as a great community. I think Esden does a great job of cultivating that community. And in particular, I'd like to give a shout out to TNT on that forum, because he's so helpful, and he's, like you say, his hardware skills are at such a high level. And then he shares on his streams in his YouTube channel and gives like great insight for people like me who want to kind of learn the next step, or what else can you do. And he's always kind of managing to squeeze impossible stuff into an FPGA, and kind of, I think it was really a live stream of his that properly helped me to understand about how you design to meet specific timing closure on an FPGA, and what's going to be your critical path, and how to think about digital design to make sure those critical paths are going to be short or quick. Yeah, so big up TNT.
Yeah, TNT and GateCat have both helped me enormously, especially with using NextPNR and Yosis to get the best out of my designs and things.
Yeah. I got a little thing on my to-do list here, which maybe falls into one of the things that you didn't understand what I was gonna talk about. But I wanted to say, on one of my graphics projects, I did in fact, I might just go and get it. I hope this works. I charged it up for the.
Oh, charged it! Oh, it's a live demo.
Oh God, with a live demo, it never works, does it? I charged it up last week when I thought we were having our interview last week, and then I was wrong by a week. And in that week, it's now discharged itself.
No.
Yeah, so
well,
I
can
made
you charge it up while we talk about other things? Oh, what's it? Oh, is it a badge from?
Yeah, so it's an Icebreaker with a microphone PMod, and then a screen here. So then if I whistle into it, like, then you can see there's like an FFT and plots that as a waterfall. And I was finding with every time I would change the code, the HDL, the Verilog, and then synthesize it and use NextPNR to put it on the FPGA, the colors would be different.
Okay.
And everything seemed to be fine on the simulation. And I eventually traced it back to needing to register the outputs. So because the logic gets laid out wherever, and then when you take like the video output, and on the LCD clock, it's looking at what the color is, but those colors are coming from different parts of logic or different lookup tables, and they arrive at a slightly different time from all over the design. And then the colors are different. And then you do a different layout or use a different seed with next PNR, and then the colors change. But then when I registered the outputs so that like right at the edge of the FPGA, they're all coming in on getting updated on one clock, that totally solved it. But that was one of these horrible simulation versus synthesis bugs. And I was wondering, is that something that you've seen in graphic stuff? And like, are there any other sim-synth kind of pitfalls that you've run into that you've got any advice on how to resolve?
Well, yeah, I had a different, if similar experience when I came to Icebreaker. So when I was doing HDMI output on my Xilinx board, because the way you had to do all the encoding and stuff, you were automatically registering the output with it next to the I/O pins. When I came to Icebreaker, I had all sorts of weird ghosting problems. In fact, my colors were right, but my images were sort of ghosting. And that's in fact where I learned about the SBIO primitive on Icebreaker. And in fact, TNT, who you mentioned earlier, was the one who was like, you're not doing this explicitly. And next PNR doesn't say, oh, well, this looks like an output. We'll put it in this register. You need to do it explicitly. So, that was really useful. And I updated my blog post to show, that and the trick of using DDR and things to get the best output. But I think there is no, simulation is never going to do everything you need it to do, even if you use say Verilator and FDL, which we might talk about in a bit. Just those things like registering outputs or dealing with timing skew and stuff, it just never seems to be quite the same in simulation. And if you get frustrating bugs, I often found if you just adding a set of flip-flops, just adding a set of registers, often just fixes the problem, which isn't terribly scientific, but things that work in simulation, it turns out you've just created this big lot of, combinational logic. And in simulation, that works perfectly. And then you're like, hang on the hardware, it's just timing is all over the place. So, so the Icebreaker exposes more of that when you actually run it.
Yeah, the tools maybe hold your hand a bit less. I was talking to a friend of mine called Diego, who's a real expert in this kind of stuff, and he was saying how there's all these kind of rules of thumb that you should use. So every time you make a module, you should register the outputs so that things all change at the same clock. And if you get used to kind of getting into the habit of doing things along these design guidelines, then you're more likely to end up with the same thing working on an FPGA as it works in the simulation.
Yeah, I'd agree with certainly with the registering outputs. I think I've only got one module where I've explicitly decided not to, and I've documented it, and it's because it's registered immediately in the logic it links to. But a lot of these rules of thumb are definitely worth learning.
Adopting,
from. And registers are cheap. I think everyone's kind of scared of spending registers on stuff, but even the Icebreaker has thousands and thousands of registers. So
one for every lookup table.
Sorry?
One for every lookup table.
Yeah, so don't be afraid. I think people are overly afraid of using registers in their designs. Yeah. I know in the past I've been maybe not generous enough with them, and I've certainly improved performance by adding them.
Break up those combinatorial pathways with another level of registers.
And especially, like I mentioned the Icebreaker before, I think it's not just the difference in tools, say, with some of the commercial products, but also because the FPGA is simpler. So I'd say some things that you can get away with on the, say, faster FPGAs show up more. So again, TNT, we keep mentioning him, but it was like, you do realize on the Icebreaker that subtraction, just using subtraction, uses a whole nother layer of logic. That's why this is performing poorly. And I was like, I hadn't even considered that. But because it needs to do the invert and then the kind of maths, which hadn't been a problem on the sort of larger FPGAs I've been using. So it improved the performance on the larger FPGAs too, but it was much more critical to get it right. So that is one of the challenges, I'd say, with video, say on the Icebreaker, is that you're more often pushing against the limits of what the board can do, which is great experience, going to be great fun. But you do need to be really mindful of timing more so than on a board with, I guess, faster logic.
So, Will, what would be your suggestion as a good my first video project?
Okay, well, I guess it kind of divides into two things you need to consider: how to drive the display you're going to use, and how you're actually going to draw the graphics. So, driving the display depends on what display you choose to use. Is it a VGA monitor, a television, or whatever, or even an LCD panel directly? So, but for a first project, I'd suggest either using VGA because it's really straightforward, or using an output that does the encoding for you. So, if you use the DVI-P mod that works well with the Icebreaker board, then it does all the encoding of DVI for you. So that's really straightforward, and it has the advantage of working with televisions and monitors that people have. So yes, and I'd stick to, don't be too ambitious with the resolution at first. Like VGA 640 by 480 is a good fit, I'd say, for the Icebreaker without too much, pushing the limits initially. People do use stuff at HD. And then there's like how you actually draw the graphics. So broadly speaking, you can race the beam in the days of Atari, and where you draw the pixels like as the sort of virtual beam passes on the screen. And this is really high performance. It works well with sprites and simple designs, but it does mean timing is a real issue. So everything you draw has to be exactly at the right time, but it works even on the tiniest FPGAs, and sprites, which are really easy to do. I've got there are plenty of examples of those in Project F and on other sites. Make for really good interactive graphics games or whatever. If you want to do something more complicated, then you really need a frame buffer, which is relatively straightforward, but you do need the memory for it. So I think one of the biggest challenges with graphics projects, I don't know, your first project what you used for memory to.
Yeah, I ended up using I used the Black Ice board that has an external SRAM, and I used that for the frame buffer. And I think I needed a frame buffer because I was doing persistent lines. As you drew with the can, those lines would stay on the screen, and you could only have like 5 or 6 lines calculated with Bressingham line algorithm before you ran out of timing. So you had to store the results of those lines somewhere. So I ended up going to frame buffer. Yeah,
so frame buffer, I'd say, is unless your project is sort of game or sprite oriented, or you really want to push the sort of metal, then I'd go with a frame buffer if you've got the RAM. And you can use like the pseudo SRAM on the Icebreaker. You can have a 320 by 240 frame buffer and room for other things.
Yeah, so that's one of the nice things about the up 5K chip that's on the Icebreaker, actually, is because it has that huge memory compared to the other chips in the same series. It's got
1 megabit.
Yeah, so you can use that for a frame buffer.
Yeah, you could use say half for a frame buffer, or half for a double frame buffer, and then that still leaves memory you could use with a Pico RB32. RISC-V core or whatever. So yes, that is a good option if say 320 by 180 or 240 works for you. And a frame buffer does give you so much more flexibility. As you said, like if you're drawing lines, drawing diagrams, visualizing or processing video, whatever, it's just a shame more boards don't have more generous, easy to use memory, because DRAM is really hard to use. So I assume similarly with if people are doing ASIC projects, then you're unlikely to have significant memory on your ASIC. You're going to have to depend on external memory. So you kind of need to look at what mode display resolution and bandwidth you need and how you're going to drive it. But you probably don't want to have to build a DRAM controller into your ASIC, or else that's going to make your life hard.
No, SRAM is much easier.
And I've made this point before. I'd really like to see more boards include, a 4 megabit SRAM, whatever. They're only a couple of dollars,
or even just a footprint. You can add them.
Oh, well, true.
Yeah.
Yeah. So for graphics, a frame buffer really does make exploring and doing interesting things easier. And also dealing with timing, you talked about the challenge with drawing lines. Well, of course, the frame buffer, if you use like BRAM, if you've got dual port BRAM, which even the Icebreaker can manage, you can write at one clock and read at another clock, then you can draw at a different frequency from, your display is operating. So that's really helpful if you're struggling to meet timing. If you're doing something complex, some complex graphics that will work at 12 megahertz, but your display needs 25 megahertz, well, that's fine if you use a frame buffer and use that approach. So yeah, frame buffers are great. Just, yeah, if you're expecting to get, 1920, 1080p HD, then you're going to need a lot of memory and a lot of boards to do that. So yeah, I think yeah, because I saw on the ASIC project you talked about recently the challenge of the amount of memory and handling, sort of sprites and things. So.
Yeah, I think there's 2 or 3 of the group submissions coming in for MPW2 are frame bufferless video displays, kind of retro gaming inspired, racing the beam. And for that very reason, with just a very small amount of memory internally to record where sprites are or what the sprite tiles are. But then everything is rendered on the fly at the speed you need. Yeah. I wanted to ask you what your preferred method is for doing simulation and testing, because one of the problems that I've had, so just going back to you, like earlier, you said it's annoying to support more boards, and one reason is because then it takes too long to do the testing. So wouldn't it be cool if you could kind of have like all your test benches and then just run them in a continuous integration environment or something like that? But my experience is that often it can take hours to render a single frame to then, say, generate a PNG and then diff that against your golden reference output or whatever. So do you have any hints or tips for... I mean, the fun thing is, yeah, you just bang it on an FPGA and look at what comes on the video screen. That's kind of one of the reasons why this makes a nice project. But if you do want to do simulation with video projects, how would you go about doing it?
Okay, well, yeah, it is really tempting. I'm sure we've all done this. We just plug in the FPGA, and occasionally it works on the screen first time, and a lot of the time you'll get a totally garbled screen. And so, yeah, I mean, I think you need a multi-pronged attack to test and simulate your video projects. So because the first tool I used seriously was Vivado, I've tended to do my initial behavioral simulation in that, just because that was what I sort of started off doing. And so my designs I tend to break them down into as small modules as is reasonable, and then test those individually, because it's really easy to write a test bench for a simple module, even say drawing a line or whatever. But as you said, I mean, behavioral simulation only gets you so far, especially with things like graphics and video. It's really hard to see if the video signal will actually work on a television or a monitor. So I've been making increasing use of Verilator and SDL combined. So Verilator is so much faster than lots of the behavioral simulation tools, that it is actually practical to do video stuff on it. So I'm still working to up the performance a bit, but for some of the examples in FPGA graphics, I'm getting around 1 frame a second or 3 frames a second, which is actually usable compared to, as you said, like waiting. I've certainly done stuff in the past where I'm like, oh, it's not working. Oh no, it's drawn 1 pixel, drawn another pixel. And that's just far too slow to be useful. So I think with the graphics, there is that huge jump from here's something I can look in a waveform to here's a million pixels being changed by something. And just the volume of data makes sort of simple behavioral stuff harder to do. You can do it for the building blocks, but ultimately you want to see, does it work on a TV or monitor? And I think Verilator and SDL is the best thing I found so far.
So just say I'm not quite hearing the acronym you're saying. FDL?
Sorry, SDL, the simple direct. Hang on, this might be something. I have to check what the acronym, but it's a what's it called? So S, it's Sierra Delta Lima.
Okay.
It's
SDL.
a well-known. Where is it? Hang on. Yeah, simple direct media layer. So SDL is a cross-platform library. It's a very thin layer on top of whatever OS you're using, which means you can, in 100 lines of C++ or whatever, get an image and draw on a screen. So what you can do, because Verilator, maybe I should explain this properly then. So Verilator can take your Verilog and turn it into C++. So for the graphics thing,
with limitations.
Sorry?
With some limitations.
Well, I try and do as little as possible in C++. But so you get an interface you can use in C++, and then SDL provides a simple interface to do graphics things. Like you can say, well, here's an array of color values, draw them in this window. And you only need 10, 20 lines of C++ to do that. So by combining them together...
So it's a bit like a very simple Qt or Cairo or something like that allows you...
Yeah, it's less about UI and more just it does do audio and game controllers and stuff. It's been used for lots of games, but it does give you basically a canvas you can draw on very simply. Sorry to interrupt you there. So, and it's also cross-platform, so you can run it on Windows and Linux and Mac OS or whatever. I plan to write a post about this because I think it is really useful approach. And even if you don't really know C++ or whatever, you can just cut and paste the example. But it does give you that quick visualization of what's going on, and you can save the things to PNGs or whatever if you'll compare it. So I'd be really interested if other people have ideas on testing graphical projects, but I think Verilator and FDL is the fastest thing I've found so far. But I would emphasize, do the behavioral tests, break your design down and do the tests of individual things. Like if you're using the Brescian line algorithm, for example, I verified that behaviorally first before I even tried drawing on
with its own
on
distinct
screen.
test bench.
Yeah, so it's just, it's not formally verified or anything, but it is, I tried to think of all the edge cases and things and found some more. Formal verification is something I'd like to learn more about, but it's just one of those things that's kind of still been on the backlog, but I haven't got to, and it's quite hard to do for some of these more complex things. Yeah. Even proving multiplication or division is quite hard.
So, yeah. I mean, I think let's not stray too far off the path here, but I think one of the things I think is misunderstood about formal is that it's very difficult to get a return on investment, and I think you can cover some bases really quickly and easily to just kind of give yourself some security that this thing will never happen, or the state machine can never get into this state, and that just, if you're finding yourself trying to work out what would happen with these combination of signals, is it ever possible for this to happen? And you can just write a single assertion saying this will never happen, and then run that through the tools and find out whether it can or not.
I mean, I'd love to do more. It's definitely something I'd like to do more of. I haven't been put off by my little experience of it. It's just that there's so many things to do and test out.
Well, when you get round to it, ask me for an evaluation license. Yosis HQ.
You see, well, one of the things I found slightly confusing, maybe again, this is off topic for this video, is understanding how the various tools in this area fit together and how the commercial and open source ones relate to each other. So
we've got a new page on the Yosis HQ website that explains that. Anyway, back onto the topic. I wanted to just share my my tip for debugging graphic stuff. So I I also have used Verilator. I'm not really a C++ person. I got a nice pull request from Daya DatP on my VGA clock that lets me run the clock in real time and adjust the hours and the minutes with buttons and save PNGs, which is great. But what I also like to do is make the VGA output and the rest of the design as parametric as possible. So I may be targeting 640 by 480, but I can squeeze it down to like 40 by 20. And then I can render a frame in much, much less time. And then I can check that frame against what I'm expecting. So, yeah, Verilator and parametric stuff. Okay, so moving on, one of the other things I liked about Project F when I was browsing through it was you've got some nice pages on algorithms or shortcuts or like how to achieve a specific thing. And I was wondering if you could just tell us what your favorite post has been so far about one of these algorithms or shortcuts.
So algorithms, you mean like division or what?
Yeah, that's a good one actually, because I was when I first started doing HDL stuff, like really at the beginning, and I needed to do a division, I just put like a divide sign in there, and then suddenly my design went from kind of passing timing with 100 lookup tables to failing timing with 5,000 lookup tables, and I was like, what is going on here? Because I didn't realize that the tools were going to synthesize me a single cycle divide. And often, so a great tip here, just before I let you jump in, is that I got shown by Claire Wolf, is you can take your divide, put it in C, compile it, disassemble it to see what the instructions are. And GCC is really great. Well, all compilers are great at optimization. So then you may find that if you do like left shift by 2, subtract some number, and then right shift, then you get the integer argument that you want. And then that's much, much quicker to get out with an FPGA. So yeah, just handing it back over to you. Maybe you can talk about one of your favorite optimizations or algorithms that you use in FPGAs.
Okay, well, I'd like to talk about division because my approach is really simple, but I think it is like very illustrative of many hardware points or hardware design challenges and trade-offs with division. So like you, when I first came to do division, I was like, oh, well, right, we can do multiplication, but division, in fact, in the tools I was using, wasn't synthesizable. And so I obviously looked on the net, and there were people saying, well, you fools, you shouldn't expect division to be synthesizable. But they didn't really provide any answers to like why or how you should go about it. Because I mean, multiplication is pretty complex as well, but seemingly my FPGA could do that. And the modules and stuff available weren't great. So in the end, I was like, well, how does division work? I went back to like school, as it were, reminded myself how long division works. And I was like, well, if I can do long division, surely it can be done in binary. And it turned out to be straightforward. So basically, I designed from scratch an algorithm that turned out to be the non-restoring I had to look that up there, division algorithm. And it's really straightforward. It only does 1 bit per cycle. So a 32-bit divide takes 32 cycles, but it's incredibly simple. The most complex operation it does is a subtract. So it doesn't use any complex multipliers or DSPs or whatever. And at first I was kind of a bit, unimpressed or disappointed with this. I wanted, faster, you say single cycle division or whatever. So I did some research, and there's all these academic papers about doing fast divide, but it's really hard, and it uses multipliers and lookup tables, and it's incredibly complex. And so, because obviously on an FPGA, I'm not stuck with just having one divider. In fact, for the graphics stuff and things I've done, I've just, I can create 32 dividers, and then on average, I'm getting, the latency is still 32 cycles, but I'm getting, 32 results every cycle. So, I think the natural inclination is to want to do things in as few cycles as possible, but because you can do so much in parallel, you shouldn't feel restricted to that. So, and as you talked about using GCC as an example to get a sense of like how complex something is, I'd say another example is to look at what commercial hardware if there are figures for it. And so I looked up my Skylake, my Intel Skylake CPU, quad core, a few years old or whatever, and how long does 64-bit integer division take? Well, it takes 42 to 95 cycles. So my trivial algorithm runs a lot slower than a 4 gigahertz Pentium, not Pentium, whatever, Skylake Core i7 or whatever it is. But I'm still getting one cycle. So I think there is a tendency for people to feel they've got to do stuff in as few cycles as possible. And keeping each cycle really simple, you get good clock speed and it's much easier to debug. So it feels like there are bigger trade-offs in complexity on hardware than there are in software. A more complicated algorithm in software, if it takes a bit more memory or whatever, you don't suffer that much of a penalty for that. But if your division logic is 10 times larger, that can be a big penalty on an FPGA or an ASIC. So
yeah, and it may be for nothing. So if you're if your target is a handheld computer game and you want fast latency, say it's got to be like a hundredth of a second, which is going to be impossible to feel. But in terms of if your thing is running at 10 megahertz and you've got to update a multiplier every hundredth of a second, then you've got tens of thousands of cycles to do that. And as you say, with an FPGA, if you need to do more than one thing at once, you just duplicate that simple division hardware and do stuff in parallel. And I really think that that's a key thing about making that next step beyond kind of the blinky hello world FPGA stuff, is thinking about how quickly do I really need the result, and how many clock cycles is that, and how can I pipeline stuff so that I get my result in time, but using the shortest, smallest, simplest possible units that are easy to test, synthesize well, and have very low latency.
And yes, the simpler the design, it is much easier to test and verify. When you mentioned division, I obviously thought of the Pentium FDiv bug, which I also looked up when I was learning about division. And that was due to they used a lookup table to speed part of the division. And when the chip was made, 4 values, I think it is in the table, were accidentally set to 0 rather than like -2 or something. And that's what caused that bug. So if that can happen to Intel with their, I'm sure, very rigorous testing, if you build a very complicated divider, like how are you going to test it? So I'd say starting simple that you can verify. If you do need to make it faster, you can, work on the optimization. But I'd really push back against people trying to do really complex, clever designs right from the get-go for something like division. So
yeah,
and
it was pleasing to see how
simply.
Go on, sorry.
No, it was pleasing to see that just taking pen and paper, as it were, and saying, how do we do division? This is, this is how you do it. Can, work wonders for that.
Yeah, that's an interesting point. Actually, pen and paper is. I have this bad habit when I'm programming to just think, I can just work this out as I do it. And then I always tie myself up in knots because I've not properly thought about what I actually have to do. But I quickly learned with FPGA stuff, there's no way I'm going to be able to solve this on the fly. And I really need to break it down into these small blocks. And then by using pen and paper and looking at it and looking at these little blocks, I think it has helped me. And now when I write firmware or software, I'm much more often to kind of sketch out what the data is and what needs to happen to it. And it kind of ends up saving me time. There was that great quote about I did 1,000 hours of writing code to save myself 1 hour of debugging. No, that's not right. Do you know the one I mean?
I think I do, yes.
I spent 1,000 hours debugging to save myself 1 hour of planning.
Okay, yeah. Well, FPGAs ramp that up, I think, to even more degree, as you say, than software. So, I mean, when you talk about algorithms, which does seem to be a really popular topic, people have been asking me to do more stuff on algorithms. Definitely, I do stuff in software first, because often these algorithms, like Bressingham line algorithm, I actually found someone else's implementation in C, and its explanation, and I based my Verilog design on that. So I felt I fully understood the algorithm before I built the Verilog version. So
Yeah,
because often these algorithms aren't that hard once you actually get your head around them. It's only like 20 lines of C or something. So even if you don't speak that particular language, you can understand it and experiment with it.
and then that actually works quite nicely for building test benches. So with the FFT display, I was using matplotlib and scipy to generate tones and check the outputs, and then that was what I could then use to test the output of the test benches against the results that I was getting from a different library. And that gives a lot of if you've implemented it in one way and then you test that against a different implementation, that gives a lot of confidence that the thing is actually working.
No, I mean, definitely. When I did my TMDS encoder for HDMI output, I wrote a Python TMDS encoder, and then I could compare like hundreds or thousands of outputs from the software completely differently implemented to the Verilog. And when they agree, you've got much more confidence that you've got the algorithm right. So yeah, and it doesn't really matter what language, if you like Python or if you like C or if you like Rust or JavaScript or whatever, but getting the algorithm sort of down in software first is I think a big important step to like having a chance of implementing it correctly first time, as it were, on
hardware.
Verilog.
Yeah.
Or on hardware, yeah.
Okay, so this has been a really great conversation. Thanks very much, Will. As a final question, apart from Project F and the 1-Bit Squared Discord community that we've already mentioned, do you have any other recommended ways of getting started or resources for people interested?
Okay, well, it is quite challenging with FPGAs, but I'd say, surprisingly, I found Twitter to be quite a good resource. Once you find the people, it's not quite the same thing as a community like 1-Bit Squared Discord, but I've met lots of interesting people and shared projects on Twitter. I'd recommend FPGAs. Is FPGA for Fun? Sorry, I'll have to find the
that rings a bell.
Right. What's it called? Yeah, FPGA4fun.com, which is a really old site that has loads of fun designs on it. I'm kind of struggling a bit to find good websites with resources on. What other things are there here? Nandland is quite good, and Bruno Levy his GitHub has lots of good things on it.
And Nandland has a YouTube channel as well. That's worth mentioning.
Yes, there are some good YouTube channels. It is a bit disappointing how there is a few gems out there, but there isn't a huge mass of content that you might expect for such a fascinating and powerful technology, I'd say. But yeah, ask on the forums. There's good stuff on GitHub.
And actually, I'd also like to mention IStudio. So this is when I've run FPGA workshops with people before, I've often started with IStudio because it's a graphical kind of point and click environment that allows you to write Verilog if you want to, but you can build up a lot of stuff with a kind of graphical schematic. And one of the nice things it takes care of is all the programming and the board connection and everything like that with a couple of simple mouse clicks. And as a educator or teacher, if you're planning on running workshops, you can put together the things that you need. So I did like a VGA experimentation workshop for a Maker Faire, and you could just click and add my set of blocks that had their own icons that was like the VGA generator, and then you could build some logic that set what the color should be at X and Y, and then connect it to the screen and press flash, and it would all happen for you.
No, it sounds great actually, because it's really hard to get that first toolchain and set up.
And Obi Juan, who's on Twitter as well, has done a lot of tutorials in English and Spanish about getting started. So I'd also recommend that. Great. Okay, Will, it's been really cool talking to you. Thanks very much for your time. I think this is going to be really interesting for a lot of people. And I would recommend Project F. So what's the URL of Project F?
It's projectf.io, and there's also, you can find it on GitHub. So all the designs at MIT licensed, so as open as they possibly can be. So yeah, go and learn and build some stuff and
do some
get
graphics.
Involved, yeah.
Cool. Okay. Thanks again. And
Thanks.
see you online.